So let's talk about some of the problems that we have in this lecture with finite combinatorics. I have to remind you a couple of things so we keep an eye on those things. First is that we have a table for number of arrangements when n chooses r, when the n is the number of objects you have to choose from, and the r is the number of objects you can choose. So there are two important things to make the difference of, which is first is whether the order mattered to you, meaning that doesn't matter which object you're choosing first, which second, which third, and so on. So I listed that as order makes difference and order does not make difference. And then, of course, what it matters also is that whether you can use repeating of a choice. For example, the first object is the same as the second object, and so on. And that we call that no repetition. If you don't have that choice, no replacement or no repetition. Replacement stands for if you choose an object and then you put it back in the set of objects you have to choose from, and then you choose it second time. Or if you have a repetition, so you can make repetition. So one way is not to have a repetition, another way is to have a repetition or possible repetition. So it's a different story here. But we said in cases when you have no repetition and the order make difference, we call it permutation. So we have this particular formula that we use to calculate permutations. And then also we said when the order makes no difference, then we have a smaller number of choices, and then we call that any kind of arrangement like that we call a combination, and the number of combination is by this formula. Okay, that's one thing. I also have to remind you that we have also multiplication principle, which means when you're making two different choices, then you can just simply multiply the number of options you have in the first choice and the number of options you have in the second choice. And here the order matters when you do that, but that's a multiplication principle. For example, we have that, how many ways you can arrange the Olympic podium with three people on Olympic podium, when you have in the final you have 8 people competing in a 100-meter dash. So we said you can put something on the first place, there are 8 of them, something on the second place, 7 of them, something on the third place, 6 of them remaining, and then when you multiply these 3 numbers, you get a total number of different choices you can have for the Olympic podium. So those are permutations because it matters who is first, who is second, who is third, right? And if that would not matter, then it will be combinations. So we have this table, so we have formula, we can calculate that. Okay, so the first set of problems I have here is about arrangements, that when you are choosing a certain number of things that you need to do with people. Okay, so the first problem, it says if you are arranging 5-passenger and 7-seat vans, and it has 4 rows of seat, but in the first row there is a driver, and so you don't have that for a passenger, so you have only 1 seat for passenger, and the remaining 3 rows you can put passenger. Something that looks like this. Okay, this is might not a really good depiction of a van, but something like that. So you have 2 seats in the first row, driver sits here, so that's not going to be for passenger, and then you have remaining second row, third row, and fourth row, all for passengers, all seats for passenger. Okay, so the first question is how many different seating arrangements you have. Okay, so you have 7 seats to choose from, so you're choosing seats. You're not choosing passengers. You have 5 passengers, they are already there, you have no choice there. But you have 7 seats and you can choose 5 for those passengers. You're going to be assigning the seat to a passenger. So you have 7 to choose from. You're choosing 5 seats. Okay? Now, can you repeat a selection? No. When you select the seat that's assigned to one passenger, you cannot select the seat again for another passenger. So, no repetition here. The next thing to ask, does order matter? Order does matter. Let me argue that. So, for example, if you have a Bill and John and 3 others, John might sit in the first row, and Bill might sit in the last row. So you selected this seat and this seat. If you put the Bill in the first row and John in the last row, and John here, you still have to choose the same seats you have chosen. But it's a different arrangement. And John or Bill or both might not like that. Okay, so you have this situation in which, okay, so we're talking about permutation. You can, of course, use a calculator for that. So if you use your calculator, you are going to have 7. Now you have to have a permutation, or you can use factorial on the top. There will be, in either case, math is a button to select, and then you go for probability option. You move by using arrows. Factorial on the top. You have random choice, permutations, combination, factorial. 7 factorial. So a large number. Divide by, on the bottom you have 1 times 2. So that's 2. Divide by 2. 2,520. Or you can just use straightforward the option for permutations. So that will be 7 math, probability, permutations, 2. And you get the same number. Oh, 7 chooses 5, excuse me. Yeah. 7 math, permutations, chooses 5, right? If you choose 2 only, that's a different story. I was a little bit deceived by the calculation here. Anyway, 7 chooses 5, 2,520 as before, right? Now, so the formula actually states on the top you have the number of objects to choose from. On the bottom you have the number of objects you're not choosing. If you're choosing 5, you're not choosing 2. So those are factorial on the bottom, and then on the top and the bottom. So you can calculate that way. You can just straightforward calculate using permutations. So, okay, there's our answer, 2,520. The second problem, or the second part of this problem says, what if you have 2 among these 5 passengers, and those 2 cannot be seated together in the same row? Meaning, like, let's call them John and Bill. You cannot put them in this row. You cannot put them in the 3rd row, and you cannot put them in the 4th row. Okay? Now, how many different ways you have when the arrangements are made when these 2 guys are not sitting in the same row? Here you will have to use multiplication principle. So you will make 2 things to get to that point. First, in how many ways you can seat these 2 guys in the same row. I'm going to calculate the number of all of different seating arrangement when these 2 guys are sitting in the same row. Once I find that number, I will subtract it from the total number of seating arrangements, because those are not eligible, right? And then I will get my number of those arrangements when these 2 guys are not sitting in the same row. So I'm asking myself a question: how many ways I can put these 2 guys in the same row? Put John and Bill here. You can put John and Bill here. You can put John and Bill here. But you can also put Bill and John here, and Bill and John here, and Bill and John here, right? So it's actually 6 different ways. So John, Bill, or Bill, John. John, Bill, or Bill, John. Or Bill, John. 6 different ways. So that's the first choice. In how many ways? You're putting John and Bill in the same row. 6. Now you need to find out, your second choice must be in how many ways you can put the other 3 passengers in the remaining 5 seats, because you already have these 2 guys in one row. So there's your second choice. In how many ways you can put 3 guys or 3 people in remaining 5 seats. That has to be the same as I was arguing in the 8th part, which is going to be 5 seats to choose from for 3 remaining passengers, permutations. Okay? Now again, you can use your calculator to find out what this number is, but I can tell you it's 60. So that will be 5 factorial on the top, 1 times 2 times 3 times 4 times 5, that's 120. Divided with how many you're not choosing. If you're choosing 3, you're not choosing 2. On the bottom, there's 1 times 2. And that would be 60. 120 divided by 2. So 6 times 60 is equal to 360 different choices for seating arrangement where you have John and Bill sitting in the same row. So again, it's a multiplication principle here. First I was choosing the row and the seating arrangement for John and Bill in the same row. That's 6 different options. And then I was choosing 3 out of remaining 5 seats for the other 3 passengers. And if I multiply that, I get 360 ways. Okay, so the total number of arrangements in which these 2 guys are not sitting in the same row is 2,160, and I get that number by simply subtracting this ineligible sitting arrangement from the total number of sitting arrangement, which is 2,520. 2,520 minus 2,360 is 2,160. Okay, so we have that. Okay, let's see the second problem here. The second problem talks about selection of a committee of 5 people from a department of physics and mathematics, or mathematics and physics, when you have a 7 mathematicians and 5 physicists. And we are selecting 3 mathematicians and 2 physicists. You can imagine yourself in a position of a dean of the school that needs a committee of 5 people from this department. So he looks at the department. I have a 7 mathematicians, 5 physicists. I need to have some kind of proportionality, so I'm going to take 3 mathematicians and 2 physicists. In how many ways I can do that? Okay. So this is actually a 2-choice question. First, you will select mathematicians, and once you find how many of them you have to select, how many choices you have to select, you have to select 3 out of 7. Then you're going to select physicists, and you're going to multiply these 2. The number of first number of options, this is the number of ways to select 3 mathematicians, and then the number of options you have to select 2 physicists. Okay, so this is like a 3 branching, so you have to multiply these 2 numbers. Okay, in how many ways you can get mathematicians? So you have to have 3 out of 7. 7 available, 3 choosing. 3 that you are choosing. You cannot repeat, so you cannot have John and John and John. That would be just 1 person. So no repetition. Also, the order doesn't matter. Why? Because the committee is not ranked. You just need 3 people. So it's not that you have, you know, well, I need a chair, then I need a vice chair, then I need a secretary, stuff like that. The order will matter. I just need the three people, uh, John, Bill, and Fred, or Bill, John, and Fred, or Fred, John, and Bill, or if you like female names, I don't know, Mary, Ann, and Catherine, or Catherine, Ann, and Mary. This is all the same, right? Three. 7 chooses 3. Okay? If you use the formula for that, you get 35. So this number is 35. Okay? In the second choice you're making are two physicists out of a set of 5. You can use the same argument, and the number you are going to have is going to be 5 chooses 2 combinations. And this number is 10. Again, you can use your calculator for either one of those numbers. So if you use a calculator, for example, first number, 7 chooses 3, how do I get 35? Of course, you can use the formula, but you can use your calculator. So, math button, move arrow to probability, combinations, third option, and then you have 3. 7 chooses 3 combinations. How many combinations you have? Each one of those arrangements is a combination. How many of those arrangements, how many combinations you have? 35. And again, you can use the formula, it will be exactly the same at the end. Okay, so you have 35 different ways. 35 times 10 is 300 possible committees. If you're selecting 3 mathematicians out of a set of 7 and 2 physicists out of a set of 5 for the committee of 5 people, you have 350 different ways to select that committee. That's the answer. Okay? I have a bunch of card tricks in this lecture, card problems. So let me just do the first one, which is kind of easy. If you're playing poker and you're dealing card at once, 5 cards, well, you can deal, you know, the first card, second card, third card, fourth card, fifth card, but it doesn't matter to me in which order, because that doesn't matter in poker. Once you get 5 cards, you can rearrange them in either order. You get 5 card hands the same way, regardless what is the first, second, third, fourth, and fifth card. It's the same 5 card hands, right? Now, to write that sample space down will be very, very difficult. Possibly do that by, you know, having something like that. Ace of Hearts. Two of Clubs. And now I'm running out of idea of something simple to draw, but let's say I have 3 of Hearts. And let's have a King of Spade. So usually written spades somewhere here. There will be 2, but I have a king here. So I'm not gonna put the person. I'm gonna put the crown, and I need the 5th card. Another ace, so it's easy to draw ace. Diamonds, ace of diamonds. All right, I can do that. Now imagine if I have to do it for all possible 5 card hands. So this would be easy if I just have this. Ace of Hearts, 2 of Clubs, if you understand what my coding is, 3 of Hearts, King of Spades. So I wanted to make spades here, but it doesn't look all that great. And then Ace of Diamonds. Okay, that's one possible coding to get. there are huge number of 5-card hands. So there is absolutely no way that I'll be able to make here a sample space. No. Okay, so I want to count this, but I'm not going to be able to do any kind of sample space drawing here. So I need to use efficient counting. Okay, now how does that work? First of all, I need to choose what you need to know what you are choosing, what you're choosing from, and how many you're going to be choosing. Now, obviously, I have 52 cards. In the deck of cards, I have 52 cards. There are 4, and then you have hearts and diamonds red. Each one of them has a 13 denomination. You have a 2, you have a 3, you have a 4, you have a 5, you have a 6, you have a 7, you have a 8, 9, 10. Ace, Jack, Queen, and King. 13 different things. So it's 4 times 13, you have 52 different cards. 52 cards. You also have to choose 5. Right? So you're making a dealing with 5 cards, right? So it's 52 chooses 5. Now the question is, can you repeat? No. In a hand, you're going to have 5 different cards. You cannot have ace of spade and ace of spade. So no repetition. The next question is, of course, does order matter? I already answered the order doesn't matter to you here. It doesn't matter what is the first card, second card, third card. You got the first card, you got the second card, you got the third card, fourth card, fifth card. The order doesn't matter. In some card games, it matters, but in poker, it doesn't matter. So this is 5-card hands when the order doesn't matter. So which means that we have our answer. It's 52 chooses 5 combinations. Okay, 52 chooses 5 combinations. Now, if you have a Texas Instrument calculator, it's easy to calculate. It will be 52 math probability, move with the arrows, combinations, chooses 5. 2,598,960. Okay? Let's say you don't have this calculator, so you have some scientific calculator. You can still calculate it because we have a formula. And the formula is how many objects you have to choose from. That's 52 on the top, factorial. On the bottom, how many you're choosing? 5, factorial. How many you're not choosing? 47. If you choose 5 cards at the deck of 52, 47, you're not choosing. Factorial. Now you can say, oh, how do I calculate this? It's really difficult. Actually, it isn't. Okay? First of all, on the bottom you have 47 factorial, which is 1 times 2 times 3 times 4 times 5 times da 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 up to time 47. That's the same thing you have here, because here you have 1 times 2 times 3 times blah 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 to 47. So you can cancel all of that out. And then you're on the top left with the 48 times 49 times 50 times 51 times 52. And on the bottom you have, I completely canceled the 47 factorial. So I have only this guy left, so which is 1 times 2 times 3 times 4 times 5. And you know what? I won't even calculate that. First of all, 2 times 5 is 10. So you can cancel 10 and this 10 here. So you have 5 left, right? I'm dividing with 10 up and down. And you can cancel more. You can cancel 3, and there is 3 here. 48 divided with 3 is 16. And you can cancel more. I'm going to cancel 4, and there's a 4 here. So if you divide with 4, you get 4 only. Okay, so that's it. I only have to multiply, well, still lots of multiplication on the top. 4 times 49 times 5 times 51 times 52. So no matter what kind of calculator you have, you should be able to do that. Or you can do that even by hand, right? Long multiplication. It's a little longer to do that. 4 times 49 times 5 times 51 times 52. We got the same number, right? 2,598,960. So you can do this with the reduction, right? Reducing to lowest terms, you have to do some cancellation of the common factors. So the answer is you have a 2,598,960 different 5-card hands. Okay, this would be even bigger number if the order makes a difference. That's why the poker is such an interesting game, because you're going to have this many possibilities for 5-card hands, and the whole game is basically about how do you get something else among those 5 cards, right? You get a second choice of dealing and so on. All right, okay, so that's my story for these pager problems, right?